I'll draw out a couple things here. Let's just do one at a time. So for nitrate, give me all resonance structures. I'm not going to tell you how many there are, just to know that, okay, there's no more after this, you know. This is how it's going to be in open.
I talk in the rain, I always sleep spray.
Very good.
Let's do another minute or two. It's 2:33 right now. Getting over here, right?
Yep.
Interesting. Where's Audie?
That's a good question.
She told me she wasn't coming.
Oh, never mind. I guess she's not coming.
Why?
She has to go home.
It's because
today.
Lil was being mean last time. She said,
You're really good at breaking promises. Okay, ready? Maria, you have an answer.
yes.
All right, tell me what the first resonance structure you did was.
So I didn't draw all three of them out, but there's three of them and they're double bonded to each oxygen. So you can have some at the end, in the middle, and then single bond oxygen, single bond oxygen. And then yeah, one more.
Okay,
And then so you can put a double bond on that one.
on which one? Left?
Just pick one.
Okay. Which one do you want me to put it on?
Double bond.
Left one, okay.
And then put two lone pairs on that oxygen.
Yeah, so like this, like that.
And then. Yeah, and then you can just do this, the little dashes to show that it could be on that oxygen or it could be on the bottom oxygen.
So we're gonna go ahead and just make another resonance structure. All right, so if we were, before we assign formal charges, let's go ahead and continue on. Well, I think what some students might have done is they may have heard at one point that the negative charge tells us how many single bonded oxygen atoms there are. And while this usually holds true, when in this case for the nitrate ion, it doesn't, because let me draw out, if we have a single negative charge, that tells us that only one of the oxygens is single bonded and the other two must be double bonded. If we were to write that resonance structure, or if we were to draw out that structure, you would have something like this. Like that. Like that, like that, like that. And what is wrong about this structure?
Nitrogen can't have an expanded octet.
Exactly, like Maria said, nitrogen cannot have an expanded octet. It only has the second energy level, which does not contain a D subshell. In this case, that means that it can only have up to 8 electrons in its valence shell. But in this case, it shows that there's 2, 4, 6, 8, 10, which is impossible for nitrogen. Not saying that it's impossible for all elements, but in this case, nitrogen is the central atom, and it's impossible for nitrogen to have an expanded octet because it's only in the second energy level, which does not contain a D subshell, meaning it cannot have an expanded octet. So this would be invalid if we put this down. So let me continue. The other resonance structure is if you watch this, guys, watch this. Copy. And then, all right. So we can remove that, remove that. You can put the double bond there, and you would have to add the lone pair there, and you would have to remove one of those. Or we could put the double bond on the right side, we would have to remove one of these lone pairs. And then we'd have to add back that lone pair to that left oxygen. Anyone have questions on these before we assign formal charges? Yes, no, maybe so. So again, the key thing here is you can't just assume that the negative one, thanks, Michelle. You can't assume that the -1 charge on nitrate tells us the amount of single bonded oxygens. Because that would expand nitrogen's octet, and we know nitrogen cannot have an expanded octet. So for formal charge rules, let's do this in blue. We know that an oxygen that has 2 bonds and 2 lone pairs is going to have a formal charge of what? Anyone want to say that? 0, right? Why do we know? Okay, so formal charge, the formula for it is the number of electrons that an element has in this specific situation versus the number of valence electrons that element has on the periodic table. So on the periodic table, how many valence electrons does it say oxygen should have? 6. Okay, so oxygen should have 6 electrons, 6 valence electrons. All right, but in this case here, if we count the amount of valence electrons oxygen has, it has 1, 2, 3, 4. Those are the oxygens. Those are the oxygens. What's it called? Valence electrons. It's the ones that the oxygen owns. And then in each of these bonds, it's sharing one of its electrons with nitrogen, right? So I'll go ahead and draw out the 2 electrons that are oxygens that oxygen is contributing, and then the 2 electrons that nitrogen is contributing. All right. So clearly, oxygen in this case has 6 valence electrons. It's contributing 2 of them in the bonds and then 4 in lone pairs, right? So this would be 6. It has 6 in this case. We don't count the red ones. We only count the ones that it actually owns. And then it's supposed to have 6. So this one would have a formal charge of 0. On the left. Does that make sense? Let's go ahead and do the oxygen on the right. All right, so how many oxygens, how many electrons should oxygen have? It should have 6, right? That's just based on the periodic table. It's in groups 6. That tells us it should have 6 valence electrons. Let's see how many it has. So it owns these 6 right here, because those are just lone pairs on the oxygen. And then it owns half of this bond, right? The other electron is being contributed from nitrogen. So again, we only compare we only look at the electrons that oxygen actually owns. So it only owns these, and it's sharing that red one from nitrogen. So that would be 1, 2, 3, 4, 5, 6, 7. So in this case, oxygen actually owns 7 electrons. So we know it's supposed to have 6. And in this case, it has 7, right? That's really thick marker. So 6 minus 7 gives a formal charge of not 0, -1. Meaning that this oxygen has a formal charge -1, meaning it has a partial negative charge to it. And it makes sense, right? Like normally you would only want 6 electrons around the oxygen atom. In this case, you have more than 6 electrons, meaning electrons carry negative charge. So if you have more negative charge, you're going to have a partial negative one formal charge. What could we say about the one on the bottom right here, the oxygen on the bottom? It's the same thing, right? Because it's a single bonded oxygen. So you'll see that once you start recognizing that oxygens that have the two bonds to them are going to have a formal charge of 0. Oxygens that have one bond are going to have a formal charge of -1. And if you see an oxygen that has 3 bonds to it, it's going to have a formal charge of +. We'll see some of those later. And you can assign the formal charges for each of these. But it would be, you see a single bonded oxygen here on the left side, so it'd be -1. This one would be 0. This one would be -1. And we forgot about the nitrogen. So nitrogen has is supposed to have how many valence electrons? 5, right? So clearly, these red ones are the ones that nitrogen actually owns and is contributing to bonding, right? There's no lone pairs on nitrogen in this scenario. So it has 1, 2, 3, 4.
How do you get?
So normally nitrogen would have 5. We know it comes with 5, right? But we have 4 in this case. So it's 5 minus 4 gives a formal charge of +1, which is what we would put here. Any questions for any people on Zoom or in person? Yeah, we're gonna do more practice and I'll pick on a random person next time. This is new, but makes sense. Good, Michelle. Yeah, so this is stuff that, so I know Dr. Armand's class has looked at, but I don't know, I'm sure Sadeghi, or yeah, Professor Sadeghi hasn't, may not have looked at it. There's no habits, right? Yeah, you haven't, but well, it's a good thing you're seeing it now. It sounds to what. But with no questions, we'll go ahead and move on. You can assign these on your own. I won't take up more time. Yeah. So props to you for coming to these sessions to stay on top of your studies. Yeah, I am her professor. Okay, the next one is going to be a formate ion, so that looks like this. You can just move the double bonds. Exactly. So double bond. I'm gonna do what Dr. Amos does and pick a random student in here to get. Do you get nervous? Do people get nervous? Like,
Made me go up front.
oh, you told me, yeah.
It's terrible.
And I'm actually surprised, he actually knows all of y'all by name.
No, he doesn't. He has a printout paper with everyone's face. and
Yeah, it's a
everything's
print
right.
out paper.
He
That's
doesn't
what you
know.
call it. I mean, you know some kids by name.
Yeah, he knows me because I'm like his favorite.
Oh, he was like calling out half the class today. I was like, what is this? You gotta get that for us.
Yeah, dude, can you imagine like the kids in the back are like showing their pants every time he does that?
Make sure y'all stay warm this weekend. He calls on like the same 5 people, but
Crazy. That's indeed crazy.
are you one of those people, Alex? I hope you are, if you want a letter of rec. Maria probably wants to hear a letter of rec.
I am gonna ask him.
Good job, Maria.
Good job, Maria.
No, I'm not. I'm not actually going to.
Does he call a naughty?
Oh, he calls on Audie all the time. Last class, he called her like almost 3 times. He's never called on me though, so I'm safe.
Okay, is Jake in here?
No,
Jake, does he call on you? If you're here, if not, then I just talk to nobody.
He called on Jake last class.
Dang. A couple of times yesterday, dang. Dude, he never called on anyone when he taught our class.
yeah.
I don't know, this next generation of incoming freshmen are very social. Or like he walked into class today and someone said, Daddy Armand, like, what?
Oh my gosh, that's Malachi, and he barks at Dr. Armand sometimes.
Are these practice problems in the exam 3 review or somewhere else? These are not on the exam 3 review. This is separate from that. I haven't started that yet just because. Yeah, I haven't started that yet just because those will go by a lot quicker because most of them are actually multiple choice questions. Because that's kind of how this exam is structured. It's more conceptual than anything else. So, well, as we learn, because obviously like the people in Sadegi's class haven't gone over this stuff. So I want to be able to teach it rather than spend one problem on this and then move to another thing, you know? You've got to make sure that everyone has their money out, as Rich would say.
You said I'm willing to be sometimes.
Okay, first resonance structure, let's see. Yeah, good job, Alexander. Okay, Maria,
Okay, so put a C in the middle
I'm putting a C in the middle.
and then. So put an O, single bond O,
Another one,
another one, and then the H on the carbon as well.
like that, or on the carbon, yeah.
And then put a double bond on one of the oxygens.
Okay.
And then 2 lone pairs on that oxygen.
Okay, and then I'm guessing 3 lone pairs on this.
And then you can move that double bond to the other oxygen.
All right, so let's assign formal charges this first time around. So Maria, formal charge on hydrogen.
Oh, it's gonna be 1, 2, and 2 minus 1.
How many electrons should,
Oh, 0.
okay, it has a formal charge of 0, right? Because it only contributes this 1 electron right here. This red one right here. And so 1 minus 1 equals 0. It's okay. I figured long day, you know. Bound to make some silly mistakes. What about the oxygen with the double bond?
Talks about that.
Every oxygen that has a double bond has a formal charge of 0. There we go. Every oxygen that has a single bond, I'm trying to be like Aguilar.
Because the moment you make a single bond to that oxygen, you should be thinking it has a formal charge of.
+1. I'm just kidding.
-1. Thanks, Alex. Alex got his money up. Yeah, so single bonded oxygens have a formal charge of -1. Double bonded oxygens have a formal charge of 0. So when you go into organic chemistry, you'll learn about pushing your electrons around. So in order to find another resonance structure, either a lone pair has to turn into a double bond, and that means a double bond has to turn into a lone pair. So I'll show you what I mean by that. So let me go ahead and kind of eliminate some of these excess things. Okay, so one of these double bonds is going to it's going to form a bond with that carbon. And the moment it forms a bond with carbon,
So that carbon oxygen bond forms. And when you form a bond to that carbon, you have to break a bond.
all right? So when you form a bond to carbon, you gotta break a bond. Oh, that was not what that's not the response Aguilar gives. Yeah, okay. So if we move one of these double bonds up here, it turns into a lone pair. So a lone pair turned into a double bond, a double bond turned into a lone pair. And I'll show you what I mean when I rewrite it. Does that make sense though? So it would have a double bond here now, single bond here, and then your H is still there. So a double bond turned into it. A lone pair turned into a double bond. We saw that right here. And then a double bond turned into a lone pair. We saw that right here. Right. So if I were to like draw out where these electrons were, you could say that this electron is here in red, and that corresponds to these two right here. And these green ones right here correspond to these that form the bond right here. So now you have different placement of electrons, and this is a resonance structure. So both of these could be something like that. Or, yeah.
When you take
Could you
organic, you'll learn
explain-
something called resonance hybrid. It's like what the atom like actually looks like in nature, not atom, sorry, molecule. Then like there are contributing structures, like one of these structures contributes more to the hybrid. So like, how do I explain this? In certain occasions, there'll be one, like it looks like one structure more than the other, basically.
Exactly. So does it make sense how we're kind of like pushing these electrons around to form another resonance structure? Yeah, perfect.
I have a
Any
question.
questions on?
So
And again, the single bonded oxygens have a formal charge of what, Maria?
-1.
There we go. And double bonded oxygens have a formal charge of what? Positive, wait,
0.
0, right? Okay, we all got that. Any questions on Zoom?
I just want to do it, I go and make a table.
Can you hear me?
Interest.
Yes, Dr. Aguilar, take it.
Yeah, he's really
I
good.
heard that.
Test our too easy. Okay, so let's do this one next.
I'm trying to talk, Kristen is trying to.
Just make sure that they're both on.
Okay. Kristen, give me 1 second to write this down so people can start on the next one. And then we'll go ahead and I'll answer your question. All right, did you put it in the chat? Oh,
Can
you
you hear
think the sound's muted? Oh, it wasn't muted, I'm sorry. This guy-
Wait, you guys can hear me now, right?
I can hear you now.
Okay, perfect. I'm just a slow typer, so that's why I'm like, I don't type in chat. Anyway, so I guess I understand, I think with like the resonant structures and whatnot, like I understand like why you move around bonds to like get different like resonant structures, but I don't know, I guess like I'm still confused why the oxygen has a single bond versus a double bond here. Because when I originally wrote it, I had like the double bonds on the oxygen and then one on the hydrogen. Then I was like, oh wait, that's too many like for the carbon. But I thought because it's like a -1 like ion that having more electrons in the structure is preferred, but maybe that's not right.
Well, you remember, you can only like, I guess, well, the biggest rule is you can't form something that, like, you can't have a carbon that has an expanded octet, right? So you
Okay.
can't form two double bonded oxygens to the carbon and then have the hydrogen still there, because that would give it 10 electrons, right?
Yeah.
So that's the big rule for second period elements. And what else did you say you didn't understand?
Well, I think that's mainly it because I didn't know that second period elements cannot have a expanded octet. Well, I actually really didn't know which ones can or can't have expanded octets, but yeah, I just kind of like wrote it out, but then I saw you explain it this way. I'm like, oh, okay. I don't know. It's not really, I'm still confused, but I don't know why I'm confused. So,
I see. Yeah, so anything that is below, so the third energy level or below can form an expanded octet, because that's when your D subshell is introduced, allowing it to incorporate some interesting bonding in molecules. But anything above the third energy level, so anything in period 2 or above, cannot have an expanded octet.
okay, thank you.
All right, sorry, let me get back to that. And if you're having a little trouble with this one, I'll go ahead and write out the first resonance structure, and then you can give me the other. Let's see how many there are. There's 2 other ones, so a total of 3. So you can do CH3. I guess I should write out all the ones. Typically, when you see a CH3, it's talking about a methyl group, so it's at the end of the chain. So you don't have to guess where the hydrogens are. So CH3 corresponds to all those hydrogens are on a carbon at the end of a chain.
Typically, right, when they give you like a Lewis structure to draw, like every atom, like in the Lewis structure is like drawn to like what it's closely connected to.
Yeah.
So like the hydrogens are next to the carbon, so they'll be connected to that carbon.
I have a quick question.
Yeah, I hear you.
Oh, okay. With nitrogen, doesn't it have 3 valence electrons?
Nitrogen actually has 5 valence electrons.
Oh,
It's-
five, yeah.
It's in group
Yeah, I
5.
meant 5,
Yeah.
but there's only 4? Or is that incorrect? Like, what's tied to nitrogen right now?
Yeah, right now it has 4 valence electrons. Meaning it would have, what would be the formal charge on that?
If it has 4, it usually has 5, then -1. Or is it +1? Ooh,
I remember
it's +1, +1.
positive one, right? Because you can kind of think that if it's supposed to have 5, but only has 4, it kind of gave one away, so it's plus, right?
Yeah,
Like-
but where did it give it away to?
Well, in this case, it would probably be like the oxygen here, it would have a formal charge of -1.
Yeah,
So in this case, it looks like it's giving it away to the oxygen.
but why couldn't you just create a double bond between nitrogen and oxygen to fulfill like the octet?
So you're saying, like, are you saying bring one of these lone pairs down here? Into
Oh, I see.
this? If you did that, then you would expand the octet, which you can't do, right?
Oh, but I thought it has to have 5, but there's only 4. Is
It
5
doesn't have to-
expanding?
It doesn't have to have 5. In the most stable form of nitrogen, it would have 5 valence electrons, giving it a formal charge.
Of
I'm not saying-
0.
So it wants to fulfill the octet rule, right? But it wants only to own 5 valence electrons. So like in ammonia. Let's do this. Ammonia with its lone pair. Each of these hydrogens contribute a single electron, right? So I'll draw those
Yeah.
in. blue. And then the nitrogen is contributing, let's see, color. It's contributing 5 here.
Yes.
While it still has a complete octet, nitrogen only owns 5 electrons, right? Because it's contributing 1 here, 1 here, 1 here, and then it owns these 2. So it
Mhm.
has 5, which gives it a formal charge of 0, meaning that this compound's really stable. But in this case, nitrogen only owns 4 of these. It still has a complete octet, right? But it only owns 4 of those electrons, meaning it would have a formal charge of +1.
But I just don't know why nitrogen only owns 4 in this case when usually it can own 5.
Yeah, so normally it would own, it wants to own 5, but in this case, the way it's bonded in this resonance structure, it only owns 4, meaning one of them probably was lost somewhere up here, or it's just the way, I'm not sure if you have to really understand why in this case it owns 4, it just, the way we drew it in this case, it owns 4. So you remember, you have to look at half the bonds, so 1, 2, 3, 4, versus normally you would want to be like this, right?
No, yeah, I get that. I guess the disconnect for me is like, why doesn't it own 5? I don't know.
I think,
It's okay.
probably because oxygen's taking 1. Or it's
Yeah.
taking some of the electrons. And also probably has to do with oxygen's really electronegative or something, is wants to withdraw the electrons from nitrogen.
Okay, I think I get it. Maybe, who knows?
Yeah. We'll do more examples and maybe it'll click with you. I wouldn't say you have to really understand why does a nitrogen in this case have 4. You just kind of have to see that it has 4, giving it a formal charge of +1. You don't have, like, it's just the way the electrons were arranged at this moment in time. Okay, so the next resonance structure, what could we do here? Anyone have any ideas? Yeah, you have an idea?
So what I did was I put,
You still have the CH3 group at the end?
yes,
Okay, so CH3. And then what's that connected to?
to a single bond on the carbon.
Okay.
And I give that a lone pair.
Okay.
And then double bonded to nitrogen, double bonded to oxygen with 2 lone pairs.
Perfect. All right, so in this case, what Maria kind of did here was, let me eliminate those. if we imagine that these electrons are color coded, not imagine it, if we say this, those are the blue electrons. What Maria did is she took these blue electrons and put them onto the carbon. So then we end up with those electrons would be here, which is a valid resonance structure. Is it probably a major contributor to the overall resonance structure? Probably not, because carbons would have a what formal charge here? Say hi with pride.
0.
0. So let's see, let's count up our stuff here. So carbon likes to have how many, Kristen?
4.
It's got 4, right?
Oh, yeah, carbon likes to.
And then in this case, it has 1, 2, 3, 4, 5. So 4
Yeah.
minus 5 would give us -1.
Wait, were you asking which the charge, I mean, the formal charge of carbon or oxygen?
Carbon.
Oh, I'm so sorry. I thought you said oxygen. I don't know how I got that.
Oh,
I thought you were asking the formal charge of the oxygen on the second structure. And I was like, oh, it's 0.
Yeah, exactly. Yeah. So this
Okay.
one, yeah, you're right. This has the oxygen does have a formal charge of 0. But I was asking about carbon, and carbon would have a -1 formal charge. And what do we know about the elements that want to have a negative formal charge? Are they the most electropositive or the most electronegative elements? So in this case, it makes, yeah, thanks Jake, thanks Maria. So in this case, or every case, the more electronegative atom wants to have the negative formal charge. So this resonance structure, while it is a valid resonance structure, it wouldn't be a major contributor to the overall resonance structure just because it's less stable. Yeah, like Jake said. And carbon is less stable because carbon has the negative formal charge, whereas nitrogen and oxygen are both more electronegative than carbon. So either of them would be happier with a -1 formal charge. This is probably a super reactive species. All right. Anyone have any other resonance structures? Anyone? Maria?
So you just do the same thing again, so there's a triple bond between oxygen and nitrogen.
So triple bonded to and wait, what's this? That would violate a lot of stuff, right?
Yeah. So
So what
single
about
bond
next?
to carbon.
Okay.
That has 2 lone pairs,
Okay.
and then single bond to nitrogen, that's triple bonded to an oxygen with 1 lone oxygen.
Yeah, oxygen.
And then, yeah, you have to put another lone pair on the carbon right there.
Okay. Oh, so you're saying one of these? Oh, and then one of those went down there. Okay,
Yeah.
I see what you're saying.
That's-
Okay. So with
This
one
one has a
more.
lot. Or is it just, I only got these 3.
Yeah, these are like the only ones that I would say as well. So what she did to get to this resonance structure is she took, let me erase all these little things here. So we got that, we got that, we got that. Okay. So she said, let's go ahead and label these here in a different color. Let's use green. So these electrons, what she's actually gonna do is she said these electrons are gonna pop onto the carbon here to give it these right here. And then these other electrons in pink on the right here are gonna make another triple bond to the nitrogen. So they're gonna kind of, I don't know, like the way after that. So like that, they're gonna plop themselves between the carbon and the nitrogen. And again, this is another valid resonance structure. It's even more unstable though. Ultra unstable for you.
The electrons are probably crying out in pain right now.
Look at that. That carbon has a formal charge of what now?
6. Oh.
-2 formal charge. You would probably never see this in nature just because of how unstable it is. But sure, it's a valid resonance structure. And this would have a formal charge of +1 because oxygens that are double bonded or have 2 bonds to them have a formal charge of what? What? 0. Oxygens that have 2 bonds to them have a formal charge of 0. Oxygens that have 1 bond to them has a formal charge of what? -1. And oxygens that have 3 bonds to them have a formal charge of what? Perfect. Thanks, Michelle. Michelle's the real MVP. Just like Katie. Yeah. How are we
Or
feeling
like
about
Katie's mom, but okay.
Katie's mom? Yeah, okay. How are we feeling about this?
Wait, have we gone over the best Lewis structure for this yet?
That's the first one, right?
The best one of all of these, but there's actually one you can make in which all the atoms have a 0 formal charge.
Oh, yeah.
Yeah.
You want to show them?
Oh, yeah. Do this carbon right here, CH3. This. Yeah, this as is, and then all you're doing is moving these electrons right here, make it up.
But it's gonna have
Dude,
5.
that's, you know what that's called?
I'll expand on that.
That's
Never mind.
this guy Rich.
That's what I was saying earlier, so.
Yeah, this guy Rich being a silly goose. It's okay.
Sometimes that happens.
To the second best of this. I'm just kidding. Good job.
Wait till open too.
Oh, yeah. I like the way he. Yeah, he's very confident. And if you're gonna be wrong, you might as well be what, Rich? Something Aguilar says if you take Aguilar, okay? You should take Aguilar. He's a very fun guy. Fun guy. All right, let's see. Let's do an interesting one. This will be D. I know I know I already said we'll go over the exam 3 review, I guess later, but it wouldn't hurt y'all if y'all started filling it out now, so that way when we do start going over it, you kind of already answered all those questions and stuff, and you can ask questions rather than, you know. Exactly, homework for the weekend, you know. It's all right. I grade your takes on assignments. Yeah, okay, so yeah, I'm giving y'all all an assignment. Do the first, okay, they're all like multiple choice questions. It's not difficult to get through. Let's just say, let's do a benchmark to do the first 10 questions this weekend. All right, if you don't do it, that's okay. You're just, I'm just saying to help your own education, you know, what we're here to do. That's what I volunteer my time here for. I don't get paid for this, you know? Let's not talk about it. It's why TA Appreciation Day, I didn't get any, not even a thank you from any of y'all.
It's not. We said thank you.
The TA Appreciation Day.
Yeah,
No, Aguilar's TA is gonna thank you every single class period
literally.
at the beginning of the class.
Getting?
Yeah,
Yeah. And they don't make exam reviews the way I do. And Rich,
They don't?
you know, they have a practice exam that Aguilar gives them to give to the students. So heart and soul into making it.
How do you know which ones are the central atoms?
So you just draw it out as it's written. So like the CH3 is bonded to the sulfur, which is bonded to carbon, bonded to nitrogen. It's a linear chain. I can kind of give you the backbone for it.
you weren't here for this part, but what I was saying, right, is like, if you're given like a Lewis structure problem, it's generally drawn out like as you're given. So like the sulfur will be next to the carbon, etc.
Isn't that least electronegative one, the center one?
Wait, Rich, can you look at this?
The least electronegative?
This one.
So
That's
Wow.
what Alex was saying, like for when you were drawing the structure, it was like put the least electronegative atom in the
Yeah.
center.
what is the electronegativity of sulfur? Because right now I know that nitrogen's at the end and it's the most electronegative.
Right.
Sulfur Yeah, okay, so 2.6. What about carbon? Isn't that like 2.4?
Yeah, I know carbon is the least electronegative compared to sulfur. Well, actually, I don't know.
So Jake said that they're both 2.6, meaning that I guess they're both equally. I mean, they both can act as central atoms in this case, because they both have the same electronegativity value, so it's okay if sulfur's in the middle here. Now, how do you put nitrogen in here? If you had put like nitrogen in the right here and then it's carbon on the outside, that would be kind of not right. At all.
Yeah.
All right, Maria, how you doing? AC, how are you doing?
I did one structure.
Okay. Give me another one.
Yeah.
Push your arrows. We'll give that a lot of no count.
What's your arrows? Why arrows?
Because
Because
it's called curved arrow notation.
yeah, you have to like show where your electrons are going, which is why up here I show
Oh.
like these pink electrons are moving down here. That's why they're there. These green electrons are moving on to carbon. It's, yeah, like you said, it's called curved arrow notation. You'll learn a lot about that. Doesn't hurt to get some practice.
Other phrases include, I will try. Keep pushing. Few more seconds.
Yeah. No, you do not. Not even close. Okay. Let's do another minute or so, because there's a lot of good problems that I want to. Okay, Maria, on this backbone right here, where are double bonds, triple bonds, lone pairs?
So I put one between nitrogen and carbon,
Okay,
and then between carbon and,
nitrogen, carbon, carbon, and sulfur.
and then 2 lone pairs on the nitrogen and 1 lone pair on the sulfur.
Okay. Does anyone else get that? Okay. All right. Is that a valid resonance structure? Does anything exceed the octet rule? All right, that's true. So let's go ahead and assign formal charges.
Can it be less than the octet rule or no?
It'd be massively unstable, but I
It's
mean,
possible, like.
Yeah.
For
like-
certain elements, like boron and aluminum. it can be.
yeah.
Did you have a triple bond between carbon and nitrogen, just a single bond between sulfur and carbon?
Yeah, you could, which is what I think another resonance structure is, which I'll get to next. So, all right. Let's go ahead and do this. So what are the formal charges on sulfur in this case? Sulfur likes to have how many? It's in the same group as oxygen, so 6, right? And in this case, it has 1, 2, 3, 4, 5. So I have a formal charge of what? +1. What about carbon?
So
0. Carbon likes to form 4 bonds. If carbon has 4 bonds, it is a formal charge of 0. And nitrogen. -1, right? Because carbon likes to have, or nitrogen likes to have 5 electrons. In this case, it has 1, 2, 3, 4. And it has half of each of these bonds, right? Because there's 2 in each bond, so 5 and 6. It'd be 5 minus 6 is -1. Someone have a question? I feel like I hear some.
Yeah. Okay, no worries.
Okay.
Oh, I'm so sorry. My mic.
It's okay. Okay, I think they needed those. Okay. All right, how about? Now, what if we decided to do something like, I'm gonna color code my electrons so you can follow where my electrons are flowing. Let's go ahead and pop this. So what do we say? If we're gonna break a bond and form a lone pair, then we have to take a lone pair and form a bond, right? So we can pop this bond onto the sulfur. And we can go ahead and take one of these lone pairs on the nitrogen and pop it into that little area to form a triple bond. So you would have, I think this is what you were talking about earlier. You would have your second resonance structure, the CH3, I'm gonna abbreviate it like that. Single bonded to an S, which has a single bond there, and now it has these 2 electrons. Or 2 lone pairs. And then we also have the carbon triple bonded to a nitrogen. And then one of those bonds contains the pink electrons. All right, what's the hybridization on this carbon atom?
Yes.
They got money. Yeah, so I don't think y'all talked about hybridization yet. But this carbon would be called something SP hybridized. Oh, that was SP. Don't worry about it yet. It's just talking about the hybridization of the bonds in that carbon atom. You don't need to know. about
Y'all
it.
for sure learn in like the next week or 2.
And if you're in today's class, you'll learn it in about 2 weeks. No,
Yeah, you learn like after.
You learn it when you take OCHEP too. Okay. Okay, what is the formal charge on sulfur? 0. 0, right? It's in the same group as what's it called? Oxygen. So therefore, if it has 2 bonds, then it's gonna have a formal charge of 0. What about carbon? Carbon has 4 bonds. 0. 0. And nitrogen. 0. 0. Do you think this is a major contributing structure to a resonance structure to the overall structure? Why, Maria?
They're all 0.
And they're all 0 and they all obey the octet rule, right? That's exactly right.
This is like the best Lewis structure you could have since everything has 0 formal charge.
Is there any other ones? I think we probably could have done another one. I'll leave this for y'all. But we could, let's just do it. Why not? Okay, so instead of going from here, let's go ahead and do something like this. Where we could move. Let's see, how do we want to do this?
Oh, true.
A triple bond, I'm thinking like a triple bond between, oh yeah, we can do that. Okay, so we do CH3. S, that's gonna have a triple bond here. And what I'm doing, I'm taking these lone pairs and making a bond to carbon. If we make a bond to carbon, we gotta break a bond to carbon. So one of these bonds are gonna make a lone pair on the nitrogen, giving nitrogen 3 lone pairs, which is super unstable. That's okay. And there. Formal charge on sulfur in this case is what?
Two, that's 2.
+2, right? So it likes to have 6. In this case, it has 4. And we're not talking about the total electrons it has. We're talking about the ones that it owns. So 1, 2, 3, 4, right? Because it's contributing 4 electrons to each of those bonds, or 1 to each of those bonds. Okay, so +2. Not ideal situation, but it's okay. What about nitrogen? -2, right? -2. So actually, when you have a formal charge of over plus or -1, that's like really unstable. So this probably would not be a major contributing resonance structure to the overall image of the molecule. Yeah. So remember, for resonance structures, we're keeping the atoms in the same areas. The only thing that's changing is the electron placement. If you change the atom placement, then you're changing the overall molecule. Any questions on that? No? Yes, no, maybe so. Okay. Let's see, you have a good resonance structure molecule in your head.
In my head, it's not too complicated.
Maybe you can
Oh, there's a class.
give them an organic thing. Like maybe with a ketone added ester group in there, maybe. Something that Maria saw in lab. I'm thinking like with the double bonded oxygen to that. Oh yeah, student ester. Ester.
This isn't a compound, this is just what I do to like. Draw it out, like visualize it. Three, four. So.
You do like a nitrile group
Trial.
connected to the oxygen right there where you have it.
1, 2, 3, 4. 5. So C5, H3, 5, 7.
I would just let them work with that structure, to be honest. They're not gonna, yeah.
Yeah, but they don't understand skeletons. C5, H7, 3, 4. Yeah, C5, H7, 2.
No, okay, I'm just gonna draw the structure out and tell them to do the rest of the structures. So C, you have 3, okay, so C. Each of these has hydrogens here, H, and then this one has that bonded to oxygen, bonded to a carbon, triple bonded to a nitrogen. Got lone pair there, you got lone pair there, lone pair there, lone pair there. Okay, draw resonance structures for this.
Yes, Michelle. Period.
Push your electrons.
This is straight up a problem we'll be given in organic, like structure like this, and this draw all possible resonance structures.
Yeah, and it's not something that you can't do now just because we say it's an organic problem. It's literally, we learned resonance structures in Gen Chem 1. We applied them in OChem 1. Sorry, I'm in your way. If you're not sure, remember, you should be looking in a region of this where there's lone pairs, because lone pairs make bonds turn into lone pairs, right? So try to only focus on a region of this thing that has both of those.
Just it's easy. I don't want to draw it out.
Let's see why Rich eventually or initially drew it using the skeletal structures, because it stinks to draw all the hydrogens, right?
While you're over there, you want to keep doing my lab report for me?
Oh, yeah. A 51% yield, what's this?
At 51% yield's good. You're right next to it.
I got an 89%.
You gotta make it somewhat cool.
You don't even put units here. You said actual yield is 4.996. What, kilograms?
I meant to, I was proof. I'm the Chico.
It was
Oh, you're
253. It was crazy. I'm taking points off of. Because we like dropped it 6 million. And then we didn't try it enough. Oh, wow.
All right. Let's do another minute or so. And it'll take some minute to draw on all these dang hydrogens, right?
Raise your hand if you have answers. I would try.
Keep pushing. Maria, are you in the honors college? Ashley,
Take Dr. Aguilar.
you're gonna understand why we say all these things when you take it. And
You
you're
guys are in the first college?
Nah,
I am.
he is. For real.
What you mean?
No, I know, I'm gonna take Aguilar. That's on my. It's on my Western list.
If you're actually not in honors college, you should try to get in it just so you can get,
I am an honors
okay,
college.
good.
Wait, does that mean you guys know who Alexis is?
Yes,
We
we
do know who
we
Alexis
do in
is.
fact know who Alexis is.
Oh my gosh, you guys know Alexis?
Yeah, she graded my exam.
Really?
she
She's
made it.
awesome. I love Alexis.
She made
Who's
errors on
Alexis?
the grades.
She's an upperclassman in the top scholar, and she told me to take Aguilar.
Yeah,
She's a
everyone told me.
TA.
to take-
Okay, Rich, go ahead, take it away.
All right, AC, give me a residence structure.
So. Everything's like the H's when they're all bonded together with the carbons, that's gonna be the same.
Copy paste.
Yeah.
Just find that though.
Where's the fun in that? Save time maybe.
All right, done. What else?
And the double bond with the oxygen and the two lone pairs, I kept that one the same. I didn't change that one.
Same.
Then single bond with the carbon and an oxygen with two lone pairs. Then a single bond with carbon and one lone pair. Then a double bond with nitrogen and two lone pairs.
Nitrogen, 2 layers. Okay, so what I'm gathering is it's something like this. So you took this, wait, there's a lone pair on that carbon?
Yeah, I moved the triple bond one over to the carbon. You can't do that?
I
Well,
mean,
you can, but you would still have. How would you end up with two lone pairs on the nitrogen without breaking another bond?
Wait a minute, you're right.
so let's say this, let's say this lone pair. So what you did is you moved this bond over to this carbon, right?
Yeah.
So, all right, what's the formal charge now on that? This one right here.
Oh, that one?
Yeah.
-1.
-1, exactly. Now what about the nitrogen?
1.
Positive. So is this a valid resonance structure?
No, because the carbon's more negative than the nitrogen, and nitrogen is more electronegative.
Well, it is actually a valid resonance structure, but it wouldn't like, it wouldn't, the resonance hybrid wouldn't look mostly like that.
It's not a major contributing resonance structure because of how unstable it is. But it is a valid resonance structure because you're only moving electrons, right? You're not moving atoms, yeah. And
So-
although the nitrogen is deficient in its octet, it's still technically a valid resonance structure. It's a really invalid, I mean, it's a really minor one though, like. Nitrogen would not lose an electron, it would not lose a fight. The carbon over those electrons, you know?
You have to check the oxygen double bonding to the carbon now. Or no?
Well, that didn't change, right? That didn't change up.
No, because like it had a lone. Two lone pairs on top, right?
Yeah, they.
And then now it doesn't have those.
Oh.
Oh, sorry, I forgot to
Sorry,
draw those.
sorry, we forgot to draw those.
Oh, okay.
Just kidding, what's up?
Is there any difference if it's like -1 or +1 for resonance? This is easy.
What do you mean?
Like the effect of how stable it is.
So you want the more negative, you want the negative formal charge to be on the more electronegative atom. That'll stabilize it. So like in this case, I mean, not this specific case, but the negative charge would be more happy on an electronegative atom like nitrogen than on carbon because it's able to hold that negative charge better because it's electronegative. All right, can I try one? Okay. So another resonance structure you could have done is something like this. So we're gonna copy. Paste. So let's erase these arrows. Okay, so you could have taken these bonds here up to that oxygen, and then this bond here on that, or that lone pair to form a bond between the carbon. So you would end up with something like this. That would remove one of those double bonds. And this would create a double bond between that carbon and oxygen. Right, do we agree on that? Yeah. All right, so what is the formal charge on this oxygen at the top right here? -1, right? That single bonded oxygens always have a negative charge, -1 formal charge. Thank you, Michelle. What about this oxygen here? Plus what? Plus two? Okay, let's count it, let's calculate our formal charge. So oxygen likes to have how many? All right, and in this case, how many does it have? All right, so it's gonna be. Wait, it has 1, 2, 3, 4, 5. Okay. So it's gonna be 6 minus the amount that it has in this case. So it's gonna give +1. And that's a general rule, right? Oxygens that have 3 bonds are gonna have a formal charge of +1. Any other suggestions?
I'm still
I
confused.
did one, but
Wait, you're confused on which one?
The one before it,
This one?
yeah,
Yeah,
or like. Yeah, what about, what's under that, like the carbon that's bonded to the nitrogen? What's under the -1? Is that one?
Oh.
I was just denoting like which carbon that was.
Oh,
yeah, but that shouldn't have been there. It's on a, he was just saying which, he was pointing out that carbon. 'Cause
oh,
there's like,
sorry.
Yeah, because I want to see how it's talked about the formal charge. I should have used it.
okay. So another one you could have done,
sorry.
go ahead.
I think I did one, but I don't know if it's right. So could I say what it is and maybe you guys like tell me if it's like on the right track?
Yeah, did you start off with this structure here?
Yeah, but I have like a thing kind of similar to almost what you did. I put a single bond on that first oxygen.
Okay.
And then I did from that carbon, I did a double bond to that second oxygen.
So like the one previous.
Yeah. And then from that oxygen, I did a double bond to the carbon.
Okay.
And then from that carbon, I did a double bond to the nitrogen.
Okay.
That's, yeah.
Okay,
I
so
had it like
that is a valid resonance structure. But the only thing is this oxygen, so it is a valid resonance structure, okay? To answer your question, but it's gonna have a +2 formal charge, so it's very unstable. Because what do we know about oxygen? Out of all these elements in this compound, oxygen is the most what?
electronegative.
Electronegative, right? So it doesn't even want to have a +1 formal charge. More or less, a +2 formal charge, it's like, heck no, right? So
Okay.
this is a very minor contributor to the overall resonance hybrid. Okay,
Okay.
but yes, you are right, this is a valid resonance structure. Okay,
So resonance
Cool.
structure, doesn't depend on the charge of like the whole things, or like, oh, it does, it's,
but what would
the charge of the whole thing wouldn't change if you.
It shouldn't, it
Shouldn't,
shouldn't.
okay, I thought it did, so that's why I was.
No, charge should remain the same because you're not changing the
Yeah.
amount of electrons, just the
Electrons.
placement of electrons.
Okay,
So like the charge on this was 0 to begin with, or yeah. So these two +2 right here, the -1 here, and the -1 here all cancel out to be a 0, right? Okay. Yeah, so, yeah, thanks, Kristen. That was another one. And there is one more, I think I saw. So if we take this original thing, and this will be the last one before I let y'all go. But you can leave whenever, to be honest. I mean, I won't cry or
No, he does. He cries himself to sleep every night if you leave.
anything, especially when you leave to go to the restroom. I'm just kidding. Okay. Okay, so let's see, you could have. Well, I think you could have just moved this and that there. And then you would have the same thing. It's kind of like what Kristen did, but you're not moving this one, you're keeping that the same. So you would have that there. And then that here. Okay, so then you would have +1 here, -1. Overall charge is still 0, right? But yeah, this is another valid resonance structure. Not a major one, definitely not, right? Because this has a +1 on the oxygen. So if anyone ever says, oh, this is not a valid resonance structure because it has a +1 on the oxygen, say, you're wrong. It is a valid resonance structure. It's just not a major contributor to the overall resonance structure. And then I'm like, what? And then say, wait till you take OChem 1. And I sound like Dr. Emma. Does he ever say that to y'all? If you take Gen Chem 2, you'll learn about this.
Yeah.
Yeah.
If you take PCAM.
Oh, he was like, I highly recommend you guys take physical chemistry. And I was like, why is he telling me to like that?
Need more chem majors in this world. Anyways, any questions? There's no questions. I did not get y'all's information and social security number last time. So go ahead, please hand me all your personal information on this little QR code. Make sure to include date of birth and everything that it asks for. Then a gift card code to Amazon. AC, I don't see you scanning my code.
I'll scan it. Oh, wrong. Never mind, I don't need to scan it.
Interesting.
I'm doing it.
All right, well, yeah, if you're on Zoom, thanks for tuning into our Friday session. Stay warm this weekend. Have a good day.
I think you were gonna do space.
Sure, I am broke. I'm not one. Same, Kristen, same. I get paid $7.50 an hour to be here. I volunteer my time, guys. Which is even better, right?
Is that true?
No, don't put that. Because I mean, it's still on the screen, and I don't like the results.
Steve,
Dude, I know. I'm just funny, like, can you tell Rich stop bullying me in the group thing? It's actually embarrassing.
Oh, no.
I don't bully
And
anyone.
he uses the same joke over and over again. It's not even funny anymore. Go ahead, say it. Say it right now.
The-
Right now.
the one
I know
like-
you want to.
Trying to figure out, we do the math to figure out who asked that one.
And then what did Alex tell you? Alex said something.